Alright, today we want to look at the question of differentiability, which is the question as to whether or not you're able to find the slope of a tangent line at a given point. Does the function's derivative exist at every point? And this, of course, depends on what we mean by the derivative. Well, the derivative, remember, is a limit. It's this limit, in fact. And so for a function to be differentiable at x equals a, this limit must exist. And for this limit to exist, we know that for any limit to exist, the limit from the left side must equal the limit from the right side. Alright, visually what does this mean? At x equals a, our tangent lines would look like that. And we know that to find the slope of the tangent line, we must begin by working with the slope of a secant line. Now we can have secants approach the tangent line from both sides. We could have points coming from the right, which would be represented by a positive h distance. So these secant slopes would be approaching from the right. We could also have secant slopes coming in from the left. So we could have a point there, for example, and our secant line might start like that, trying to get it through there, and this would represent a negative h value. But the point of these limits is that no matter which way I come from, the blue line or the green line, those secant lines must all be approaching the same line, which is the red line. So if I come in from the right, my secant line must approach the red line. If I come in from the left, the point gets closer and closer, the secant line must approach the red line. They must all smooth out to be the same slope. So the way we say that is we say that the slope coming in from the left must equal the slope coming in from the right. In some books you'll see this idea represented as the limit as we approach a from the left side, the slopes must approach the same on the right side. Okay? Alright, one more point regarding differentiability, and that is that for a function to be differentiable, it first of all must be continuous. You can't have a differentiable function without the function first being continuous, which kind of makes sense. There must be a point at a given place, and it must be connected around it in order for the slope of a tangent line to exist. And that is implied in the definition of the derivative, that the continuity at x equals a must exist. There are a couple of common situations in which we have functions that are differentiable or not differentiable. The first one I just mentioned is when you have a function that's not continuous. So if you have a hole in a graph, or if you have an asymptote, function cannot be differentiable here at x equals a or at x equals b because, as we said, there's no point at that spot. The function is not connected around it. To be differentiable, the function first of all must be continuous. So that's situation number one. Another situation is where the function is continuous. So I'm going to take a graph like this, and let's narrow in at this point x equals a. The function is continuous at x equals a. However, if I apply my derivative limit, and if I take a secant slope from each side, as this point moves closer and closer here, the secant slope is approaching and in fact remaining as shown there. But if I come from the other side, the negative side, and make h close to 0, the slopes are approaching and staying as shown in green. Are the green and the red slopes approaching the same slope? Are they smoothing out to be one line at x equals a? No, they're not. So what you'll find in general is that sharp points on graphs are problems generally for differentiability. Okay, those sharp points are often called cusps, and they are points where the function is not differentiable because the slopes coming from either side are not approaching a common slope at the point that we want the tangent to be at. Third situation is one of the vertical tangent. So if I draw a graph something like that, and I start examining the point right here, x equals a, intuitively, I can't have a slope of a vertical line, which is what I essentially have here. So the slope doesn't exist, the derivative doesn't exist. Looking at it more specifically in terms of the secant slope approaching from both sides, if I take a point here and I bring the blue point closer and closer, I can see that my blue secant slope is approaching infinity. If I come from the other side, I can see that my blue line slope is approaching infinity. Infinity does not exist. The slope does not exist, so the function is not differentiable at places where there is a vertical tangent. So to conclude, when you are checking for differentiability, the first thing you need to do is check, first of all, whether the function is continuous or not at x equals a. If it's not continuous, there's no point checking any further. If the function is continuous, then you need to check as to whether the derivative from the left at a is equal to the derivative from the right at a. If it is, the function is therefore differentiable at x equals a.